Quick last minute.
Quick last minute change. Well, all right. Okay. So welcome everybody. Let me click OK here. Uh, Welcome to today's ICE seminar. So we're very happy to have Ben Bloom here today, who's the founder and chief technology officer at Atom Computing, where he leads the technical innovations and engineering teams, building atomic array quantum computing technologies based on neutral atoms. Ben has worked on various quantum technologies and founded Atom Computing in 2018 after realizing neutral atom systems offer the best path to large-scale quantum computing. He's holds a bachelor's degree from MIT and a PhD from physics from the University of Colorado Boulder, where I think that's accurate to say he basically built the best atomic clock to date. Is that a good representation?
It
And
was at the time the best,
at
maybe.
the time, yes. He's co-authored several scientific publications and has really innovated in the atom kind of technology and holds multiple US patents. So with that, please go ahead.
Thank you. And thank you for inviting me to talk and allow you to tell you a little bit about what we're doing at Atom Computing, and specifically how we're trying to turn neutral atom systems from, noisy intermediate scale quantum systems into useful quantum computers. So I'll give a little background on Atom Computing first, since probably most people have never heard of it. So Atom Computing is a company I founded in 2018. We have two main locations, one in Berkeley, where we set up our first prototype machine, which I'll be telling you about. And then about 2 years ago or so, we actually opened a location in Boulder, Colorado, where we're building new machines based mostly off of a different atom. But I'll explain why we went from one atom to the other in a bit. As well as having satellite offices growing up in the pandemic and hiring people in North Carolina and Austin and all these other places. So we build machines for external access or otherwise based around alkaline earth-like atoms. We have about 65 employees. 25 of those are actually AMO physicists, and about 80% of those employees, I think it is, are all technical. And then we have, another 10, 20% that are business focused, accounting and support staff and things like that. So what are we doing with neutral atoms? Obviously, not everyone in the world, but many people in the world are trying to build quantum computers, and they're trying to do it along many different paths, whether that's superconducting qubits or trapped ions or neutral atoms or even topological qubits or things like that. And essentially, everyone is after the same properties, regardless of the actual physical platform they're using. So they want very, very high quality qubits with very, very good coherence times. They want to be scalable to many qubits. It's not good enough just to have some very good, nice qubits that you can have tens of. You really want to have something that you're convinced can reach into the hundreds of thousands or millions, or something that you can network up to those levels. And finally, you need a universal gate set. And one of the amazing things about neutral atoms is that if you go back to some of the proposals for neutral atoms way back in like 2001 and things like that, neutral atoms didn't necessarily have all of these things in spades. And it's only in the last decade or so that things have really turned around for neutral atoms. So first and foremost, we've been able to get to incredibly long coherence times. And actually, where atom computing was one of the first to be able to achieve something on the order of 20 seconds coherence time using these nuclear spins qubits. We've, in addition to that, been able to actually do very high efficiency readout with very, very low loss. There's been multiple groups working on scaling. I'll talk a little bit about our approaches to scaling, which have now pushed us over 1,000. And in general, figuring out how to scale the optical control as well, which we've been working with University of Washington and other partners on, including Sandia. And finally, the universal gate set. In the last few years, there's been an amazing progress on Rydberg atoms and 2Q gate fidelities. And I'll showcase some of our results at Atom Computing, but it's a huge field with tons and tons of people in it. I tried to list some of the people who are actively pushing on this field, whether they're at companies or they're at academic groups. I think there's just lots and lots of people now pushing on neutral atoms. So one of the cool things about neutral atoms that is not true of every other platform is that it really gives you access to what I would say is novel architectures. So things I'll talk about a little later on is that you can actually do 2-qubit gates incredibly, incredibly fast in neutral atoms. So I'll showcase 2-qubit gates on the order of 80 nanoseconds in length. And that's 80 nanoseconds compared to the base coherence time of many, many seconds. So you can get to incredibly, incredibly dense circuits where you have some amount of serialization of 2Q gates is actually totally fine because the idle errors are quite low. In addition to these kind of fast gate approaches, you can also think about playing games with the Rydberg atoms or how we arrange the atoms. So people have looked at how to, fit LDPC codes on atoms using different kinds of Rydberg states to control which 2-qubit interaction you're actually trying to perform at any given time. People have also thought about, well, is there a way to actually move atoms around in a very parallelizable way that allows you actually to recreate some of these LDPC or bicycle codes? And then finally, there's also tons of work being done, I would say, in the next few years on network architectures. So I think we're of the opinion you can build very, very large systems with neutral atoms, but to get to, ultimate utility scale, you probably do need at some point to connect different machines together. And one of the nice things about neutral atoms, and as well as ions, is that there's already a very unique and easy way to actually bridge the span of the qubit frequency to an optical photon, because these things are already optically active. And of course, there's been lots and lots of excitement around what I would call parallelized all-to-all connectivity. As you take many of these same properties, the fast gates, the ability to move atoms around, and I'll show us other kind of trapping techniques, and you kind of combine them so that you can pick up and place huge numbers of atoms simultaneously into different zones and actually allow yourself to do gates in one zone, readout in another zone, and so on and so forth. And I think all of these together are kind of unique, I would say, to neutral atoms. There's like variations on these same things and various different platforms, but with neutral atoms, there's almost a infinite amount of choices you can make on the kinds of systems you want to build. And so it's an exciting platform to build off of. So now that was kind of an overview of what everyone's working on, but I want to talk a little bit about what atom computing has been working on. So I'll tell you a little bit about our first system, our prototype, and how we're turning it into a quantum computer. I'll tell you a little bit about the work we've been doing to get past one of the main challenges that neutral atoms have faced, even in recent publications, which is mid-circuit measurement, where we lose very, very few atoms and we kind of disturb data qubits, or sorry, we try not to disturb data qubits. I'll talk about how we've now figured out a way to scale to above 1,000 qubits and in a way that we also think can continue to scale. So it's not just about getting to 1,000, but building a platform that we think we can keep engineering to get to 10,000, to get to 100,000, and so on and so forth. And then I'll finally talk about some new exciting results that are new about nuclear spin qubits with very high fidelity 2Q. So what does our first generation system, our prototype, look like? Well, as you can see, the prototype system looks like every other neutral atom system in any academic group in the world. There's nothing wildly special about this system. At the time, it was one of the first systems in the world to trap individual strontium atoms, and I think it might still be one of the first to trap individual strontium fermions. But in the end, it's a very flexible system that allowed us to get going at atom computing. And it's much more like an academic system. Everything was hand placed. There was a few different places where we were very careful and catted things up, but it was a much more academic-like system. If you zoom in really close, what you'll see is we were using a glass cell. And this is kind of the magic of the last few years, which is that we can create this very, very high vacuum environment, put the atoms in a glass cell, and actually, because the glass cell can be made so small, you can actually use not standardized microscope objectives, but specialized microscope objectives just to get a lot of spatial resolution on how you create the traps and how you manipulate those atoms. So what is a nuclear spin qubit and what are we using? To begin with, we started with strontium-87. Strontium-87 is one of my favorite atoms, having built clocks with it. But a lot of people say it has, one too many electrons compared to an alkali. In general, this means this one too many electrons problems is really creating a very rich landscape of different energies that you can actually play with. So there's dipole allowed transitions, which are pretty broad at 30 megahertz, which allow you to cool the atoms from millikelvin from Kelvin down, or hundreds of Kelvin down to millikelvin. There's transitions at about 7.5 kilohertz, which are much narrower and allow you to cool the atoms from millikelvin down to microkelvin and manipulate the nuclear spin, as we'll talk about in a moment. And then there's finally this amazing transition, which, many, many hundreds of terahertz away, is giving you another set of very, very stable states, this so-called clock transition, that decays for usually other reasons than its natural lifetime, but usually decays because of the way you're trapping these states. Now, how do we actually create a qubit with that? Well, actually, strontium-87 is a pretty poor atom to try to create a qubit with. Potentially, you could create a qubit with it with 10 levels. But for us, we really wanted to start off, there was a lot known about the kind of Rydberg structure in strontium. And we wanted to start off with something where we were certain that the Rydberg structure was going to be amenable to 2-qubit gates. So even though we did start off with strontium-87, we really needed a way to figure out how to actually turn this 10 nuclear spin state system down here in the ground state to a qubit level system. This should be familiar to kind of people who've dealt with this before. But in general, we have to figure out a way to manipulate this nuclear spin, to read out the nuclear spin, and finally to couple these nuclear spins of different atoms using a Rydberg interaction. So how do you actually get to individual atoms? The amazing thing that's changed since about 2014 or so is the kind of ubiquitous use of optical tweezers. What we essentially do is we take a large cloud of neutral strontium, we get it into a vacuum chamber, we cool it down to microkelvin temperatures, and we just focus laser beams really tightly across this cloud. And these very, very tightly focused laser beams allow you to attract atoms to the high intensity regions if you're using a red to trap. The cool thing about this is you don't need to have a single laser for every single one of your traps. You can use holography, for example, to create many, many dipole traps using a single laser. You can do this and actually create thousands. I think the new record is to create something on the order of 10,000 traps and a trap about 6,000 atoms in Manuel Andres' group. But this is a very, very stable platform, and it's very, very simple. Even though this diagram looks quite complicated, at the end of the day, we're just taking one laser, we're taking a computer-generated hologram on the spatial light modulator, and we're writing the pattern of hundreds of traps. Now, when you do this, you can actually trap either 0 or 1 atoms inside this, you can either trap 0 or 1 atoms inside each one of these tweezers, and you start off with this completely, almost randomly filled grid of atoms. Of course, you need a defect-free array or defect-free quantum register. What you can then do, because the atoms are so long-lived, you can actually take your image and then feed it back onto a computer where you can actually control another set of dynamic tweezers, which allow you to pull atoms to wherever you need to be, or wherever they need to be. So this is actually a non-real-time situation, what you're seeing right here. In fact, in reality, what you'd actually do is you take one picture, you do all the moves, and actually the next picture is right now, where you actually have the fully filled array. But what we've done here is we've kind of slowed down this process and demanded that we take a picture each time. And I think if you look at what it looks like without any kind of image filtering or anything like that, it looks about that, like that. So now that we can create these, nice arrays of neutral atoms, the question becomes, if we want to use a nuclear spin state, how do we actually read it out? In this first generation machine, we did a bit of a dirty trick, which is that we used our, neutral atom quantum computing system as one of the world's worst optical lattice clocks, or an optical clock. You can actually manipulate these nuclear spins using this optical clock laser, and you can actually shelve one of these spins, such that that 461 nanometer light does not interact with the shelved state. And by doing this, you can actually very easily just measure one state or the other state, or you can do some repumping and just measure, in a state agnostic sense. But this allows you to kind of utilize this metastable state to do nuclear spin readout on strontium. And we'll talk a little bit later about a different way of doing this on ytterbium, but this works well enough for strontium. Of course, you can do this and you can play games and you can double check that you're doing everything right. And I'll talk a little bit about how we actually prepare this set of atoms, but you can take images that are red or images that are blue, and depending on how you've actually set up the system, you can do readout, so zeros and ones show up in the various places. Now, how do we actually do the 1Q gates? The 1Q gates we do with 2-photon Raman. The interesting thing here is that you can't actually be infinitely far detuned from these intermediate states with these nuclear spins. The nuclear spin qubit itself is very, very well protected from its environment, even to the extent of it being difficult to actually do the 1-qubit gates. But that's kind of a nice property of it. In the end, this means that the qubit itself is very, very stable. State prep can be done by utilizing this hyperfine splitting in the upper state and actually being able to just repump in one direction or another. And finally, we just encode the qubits on the -9/2 to the -7/2. To finally break the degeneracy, though, what we can do is once again use this hyperfine structure up here to actually do some almost quantum engineering, if you want to say it, where we actually take another laser beam and kind of shift or break the degeneracy of the ground states. So instead of having equally spaced nuclear spin states from -9/2 all the way to +9/2, we can kind of just break this degeneracy by doing this Stark shifting, and all of a sudden our 10 qubit system becomes a nice qubit system right here. And of course, we can do this on the 1Q side. We could do it with a global beam, but what we actually do is we do it locally so that we can have arbitrary single qubit gates on any atom. And this just allows us to essentially do just arbitrary gates, just like you would in a superconducting qubit processor, where you have virtual Z rotations and things like that. So now we have this additional challenge of keeping optical potentials and optical addressing light aligned to each other. But one of the nice things in this system is that they're all going through the same microscope objective, so that a lot of the movement of the atoms with respect to these beams is actually very, very common mode. Of course, this is like slightly old data, but or maybe this is very old data, but what we can do here is we can actually just perform 1Q randomized benchmarking, tune up the system using RPE and other techniques that are kind of common to quantum computers in general, and we can get a nice distribution of optically addressed qubits, except for this one down here, which must be a bad qubit. But in general, I think that this is old data, and most of the time we get rid of these defects or something like that. Now, how do we actually do 2-qubit gates? 2-qubit gates, we want to try and figure out a way that kind of maximizes the efficiency of your neutral atom system. And to do this, we actually utilize what we call an interaction zone. So the cool thing about an interaction zone is because we have slightly arbitrary control of which atoms go where in the system, we actually have all-to-all connectivity. So by moving the atoms into this interaction zone, we can actually perform a nuclear spin specific rotation using the clock, put the atom into triple P naught, and then perform a very, very fast entangling operation using a UV laser. And with these two things essentially happening in the interaction zone, the other atoms actually don't care. And you can actually place these, depending on exactly the traps you're putting them in, you can place these in either close in or far away, depending on various Stark shifts and things going on here. And the other cool thing is that you can now do multiple 2Q gates in parallel. So as long as you create many, many sites here, you can do all these steps in parallel, and you just make sure you fill these sites up and then let yourself run. Now, of course, the unfortunate thing about this is that while we used to have these beautiful, very simple circuit diagrams, we now have lots of rearrangement in our system where we're pulling atoms into and out of the register, and these circuit diagrams become a whole lot more complicated. Now, in this prototype system, the 2Q gate's mostly limited by laser noise on that UV laser, but you can do pretty much arbitrary circuits, and we have some customers and potential partners that we've been having running on the system just to play around with our kind of programming environment and stuff like that. But you can create Bell states, you can create larger states like GHC states, and so on, and this keeps going ad nauseum. And of course, we're always interested in trying to make the prototype system work at a higher fidelity, though as we'll see, we're now much, much beyond the fidelity of our prototype system with our new systems. So what are we doing differently on our new systems? So our new systems transitions from strontium to ytterbium, and the reasons are mostly about speed. Strontium utilizes this fairly narrow, that's not the triple P1 transition at 7.5 kilohertz. While it has kind of amazing coherence properties, the readout, which we can do non-destructively, is still slow at the tens of milliseconds timescale. Whereas with ytterbium, there's a different set of line widths. And that different set of line widths, even though it's only a subtle change between strontium and ytterbium, make the difference between speed for our single qubit gates, or sorry, for our readout. And finally, ytterbium is this other nice property, which is that it's spin 1/2. And we'll talk a little bit about how that actually opens up the door for much, much faster gates. So the ytterbium systems were built after a few years using strontium. So we now had significantly more people at the company. And we also had a pent-up list of all the kinds of ideas we actually wanted to implement. We had started off a very simple system that was very similar to academic systems, but we had lots and lots of ideas about how to make it better. And so in this second generation system, instead of stripping away complexity, we've maybe added less, or we've taken away flexibility, but we've added a whole bunch of complexity. And from that, we've been able to achieve some pretty cool things. So first off, we focused a lot on modularity. So the systems themselves, I don't know if I have a picture of them, are now all catted up and all built off to the side. You get to actually make sure that all your subsystems work exactly the way you want them to, and then you can go and install those onto the system itself. The vacuum chamber is a fair bit more complicated. However, it comes with both new and exciting design constraints, and also these new design constraints create new opportunities. So in this example, what we have is a system that runs with no changes of the magnetic field whatsoever. So atoms start in a very, very high oven just by heating up a block of ytterbium. They flow down, just like they did for the strontium system, through a 2D magneto-optical trap. They get collected in a bottom chamber, which is actually invisible. It's actually below the table right here. But they get collected in this bottom 3D magneto-optical trap, and we use actually a special kind of trap here that fluoresces very, very low amounts of light. And then those atoms are actually dragged upwards about 30 centimeters or so into what we would call the science or compute chamber. We do some really complicated work where we're actually moving lenses and we're at the same time chirping lattices and things like that. And what that allows us to do is move the atoms incredibly quickly across this 30 centimeters from the magneto-optical trap to this compute chamber. And we can move about 90% of the atoms or so. Although at the end of the day, we almost never need that many atoms. So we operate it with very, very much less than that. One of the cool things about having this be at a constant magnetic field, and also having this special, actually for this we didn't use the special purchase mod yet, but having this kind of long 30 centimeter distance, is that we can actually run the magneto-optical trap simultaneously with having atoms having good coherence properties in this upper part of the chamber. This allows us to have something like a loss of contrast of essentially 3 plus or minus 2% per second. Since then, we've actually changed the magneto-optical trap to something that fluoresces, I think it was a factor of 1,000 or so less. And so this number is probably on the order of much less, probably not a factor of 1,000, but much, much less now. This allows you to essentially start playing games where you can essentially keep a set of cold atoms here, maybe actually play a game, as we'll show, where you reload a set of cold atoms into reservoir traps and actually build up very, very large sets of neutral atoms, which I'll show off in a second. Now for this nuclear spin in ytterbium, we have this nice spin 1/2 property. And also we now have this much, much broader 180 kilohertz transition triple P1. We utilize a different kind of magic wavelength where the ground state and the excited state have equal polarizabilities. And we do this on the stretch states. Hopefully in the next, we do this on the stretch states. That's at the triple P1 minus 3/2 and the triple P1 plus 3/2. And these ground states all have the same polarizability. We just use a very, very large magnetic field, which is a little bit of a brute force trick, but it turns out it's a trick that works incredibly, incredibly well. Even with we can now address just cycling transitions. We don't have to do any of this metastable readout. So we can just turn on light that's at sigma minus and detuned by this amount away from the sigma plus transition. And we can get very, very clean images just at the 0 state. We can do actually the same with the sigma plus and get very, very clean images of the 1 state. And even with our collection efficiency of just a few % of the light, we can now do imaging almost 8 times faster at about 5 millisecond images and collect about 30 photons collected. And in the future, one of the things we'll also be doing is trying to get this 30 photons essentially down. We have some background amount of light, but I think if you're after about 3 nines of readout fidelity, you don't really need to collect 30 photons. If your background noise is low enough, you should be able to collect just something like 7 photons. In addition to this, we have something on the order of a percent level loss and a part per thousand level infidelity and spin flips caused by the exact way we've actually created this magic condition up here. But in the future, we'll probably improve that to push that down even lower. I think if you now want to see just a whole bunch of zeros, which are the good side of zeros, we can start to calculate, errors in this, and we can see that things are quite nice. This new scheme that's a little bit of a brute force trick, but this brute force trick works incredibly well. So now when we talk about site selective imaging, how would we do mid-circuit measurement in a neutral atom quantum computer? Because this is one of the main challenges of neutral atom quantum computers, is that you're able to create these very, very dense arrays of neutral atoms, but it's not just the imaging light you have to worry about. It's actually the light rescattered by atoms, hitting other atoms nearby, which can cause spin flips and can actually ruin your mid-circuit measurements. So how do we either direct laser light only to the subset of atoms that we're trying to read, or how do we stop these atoms that we are reading out from affecting the atoms we don't want to read out? Well, one of the cool ideas we came up with was taking that same Stark shifting idea we had for the ground state strontium system and applying it to the excited state of our readout transition. So essentially something we call hiding. And what this does is it allows you to very, very power efficiently push on this excited state just enough that you can turn off essentially the imaging light or the action of the imaging light on the atoms you don't want to read. And one of the cool ideas here is this, that you really are pushing on states that you have no population on. And this is a very critical idea that worked out very, very well for our strontium system and allowed us to create the qubit. It's that we're essentially creating Stark shifts on states that don't have any population when the system is performing correctly. And that combination allows you to actually have very, very efficient Stark shifting. When we do this, we can now actually we can Stark shift the atoms away. There could be data atoms for any kind of neutral atom, quantum error correction code. It does cause some shift by flooding the atoms with detuned light. And there are some ideas about how we can correct that later on and reduce that shift. But you can also echo away that shift by playing games with just echoing. At this first iteration of this, which we published, I think, about last year, one of the cool things we showed is that the contrast reduction is about 1.3%, very, very close to this almost like 99% readout fidelity. Since then, at the time we were running this, we were limited by our choice of lasers. Essentially, our choice was the lasers we had versus the lasers we ordered. Since then, we've actually received the lasers we've ordered, which could actually push in a much more effective and efficient manner, which would also decrease this contrast reduction significantly. And one of the other cool things is there's just very, very minimal impact on the actual sites you're actually imaging. So you can see that these atoms that you're imaging versus the atoms you're essentially not doing this mid-circuit measurement on, just doing another protocol on, there's almost no difference whatsoever. Again, the other idea is just checking that, how this actually works with that contrast loss and, what are the essentially scaling laws and how can we get better and better with future systems. And again, many of these projects or many of these improvements have actually already been done since this initial study. So now the question becomes if we can do single qubit gates. I showed you a little bit low fidelity 2 qubit gates. I've showed you systems with on the order of 100 atoms or 100 tweezers or 200 tweezers or so. The question is, how do we actually scale neutral atom quantum computers to be at a large enough level that we're not essentially always power starved and we're not essentially always dealing with the fact that lasers never quite work the way you want them to work? And the answer is actually building off something I did in my PhD. In my PhD, I worked on optical lattice systems where we would create these potentials we would trap atoms in by bouncing lasers back and forth across mirrors. And one of the things that we did when we really needed very, very deep traps, or essentially a very, very large lattice, was instead of just trying to deal with higher and higher and higher power lasers, was instead to build what we'd call a kind of combination system that uses build-up cavities. So what you see here is this very, very complicated system of 8 mirrors, which are giving us full, essentially, or full tight confinement in all 3 directions on the system. And in addition to this full tight confinement, the other cool thing we're adding here is an entire tweezer setup. So we're trying to marry the optical lattice clock technology or optical lattice technology that existed for decades before, and this new tweezer array technology into a system that's some hybrid of a quantum gas microscope and a tweezer system. And we can do this by using, again, these build-up traps. So what does this look like in reality? Well, we actually work with outside companies. We actually do all the alignment and optical bonding and stuff in-house. But we build these very, very precisely aligned multiple cavities in a single ULE spacer that allows you to kind of overlap cavity modes on the order of about a single micron by being very, very careful about the way you're actually doing the building. And by doing that, we're actually able to create essentially very, very deep traps and have fidelities of readout on the order of 99.95%, where we can quickly say whether there's an atom or not an atom inside each trap. And it's a very nice, cool way of kind of building very, very large numbers of traps. And when I say very, very large numbers, I think the thing that I haven't put here is that we're not just creating hundreds of traps. We're actually creating, if you count in all 3 directions, on the order of 300,000 traps that are deep enough to trap atoms in. So we see this as a technology that's not just good to create 1,000 atoms, but we see this as a technology that essentially keeps building on to create even larger and larger systems. So now what do I mean when I say create even larger and larger systems? Well, one of the cool ideas of having this separated section between a MOT in the downstairs and a kind of compute region in the top is that you can really start to imagine a system where what you're doing is you're replacing atoms as they get lost from your system. And the atoms are going to get lost for a few reasons, whether that's 2-qubit gates, whether that's the tiny amount of loss due to readout, or whether that's just background vacuum collisions, because there's still hydrogen in your vacuum system that's able to kick out these very, very ultra cold atoms. So we essentially want to build a system almost like a 1D differential equation, where we're slowly adding atoms into the system by transferring them up, transporting them into a reservoir, bringing that reservoir over, like right here in this picture that we've actually taken, and then filling up our compute. And we can do that fill up of the compute in a completely arbitrary way, so that if we run for very, very long, you can see, there's an atom missing right here. But the next time we run, when we bring up a new set of atoms, we'll just replace the atom that got lost there. So again, we bring the atoms up, we put them into this reservoir off to the side. The reservoir does some light-assisted collisions, and then we swing the reservoir over. And we can get the Raman sideband cooling, or because the cavity is so deep, we can have the atoms in this cavity lattice be incredibly, incredibly cold. So what does this look like in practice? I think this is a few months old, but this is what it looks like in practice. I don't know if this is real time or slowed down, but just in general, we keep loading, bringing over new atoms from the MOT, put them in here, and then load to the right, and just load from the right to the left, until finally it's just trying to load some of the pieces that are missing. And the other cool thing is that you can do this, you can show it starting from nothing and just staying at a constant, or you can just keep the system running and you can show what is the kind of average occupation of atoms in this optical lattice at the kind of almost essentially what is the state prep for every single qubit in your system. So I mean, one of the cool things we're doing here, though, is trying to build off of this. So now we have a system that can do mid-circuit measurement. Now we have a system that can create 1,000+ qubit systems. But now we really need to focus on what is the best 2-qubit gate we can do. Because the last thing I showed you showed about a 96% 2-qubit gate. We've probably learned significant amounts since we bought those lasers and things like that. And we kind of wanted to show that off. So what do we do here is we actually have 2 systems in Boulder, one pushing on integration into 1,000 atom systems, and the other kind of spearheading efforts towards the highest fidelity 2-qubit gate they can make. They kind of started this spring. So we do the same interaction zone to start off with, which is to say we create this array of register atoms. We have a tiny interaction zone here. We've actually played with larger interaction zones. It doesn't really matter now, but we can create an interaction zone and we can just focus on this pair of atoms or many pairs of those atoms and saying, well, if we have a local clock and a local UV, what can we do and how good a 2-qubit gate can we create? It's a very similar structure to what I showed you in strontium. We again have a 0 and a 1 in the ground state. We do a clock rotation up to triple P naught. We do a UV rotation to this different Rydberg state, but approximately the same is actually what we're doing in strontium. And then we bring it back down with another clock rotation. Unfortunately, this means the clock shelving has to be very, very good, because essentially now our 2-qubit gate in this iteration of our system involves 3 different pulses: a pi pulse, a multi-pi pulse on the 302, and then a pi pulse back down. So what does it look like when we start talking about clock shelving? How well can we really do? At our current operating procedure or current operating parameters, we have about a 400 millisecond lifetime for that clock state. There's things we can do in the future that could probably push that up on the order of about a magnitude more to 4 seconds, maybe getting close to 10 seconds, but that's a little dicey. I think the actual natural lifetime of that system is around 20 seconds. So that's the fundamental limit, but you also have to deal with engineering constraints. Now, the interesting thing about clock shelving, though, is that it's a much different regime than your 2-qubit gates or your UV pulses or entanglement pulses. So you're doing this usually very slowly in a Doppler-sensitive way, and you do it essentially deep within the Lambda-Dickey regime, such that you try to get rid of this Doppler sensitivity. But all of a sudden, when you do that, you're actually now you're going to have to deal with motional effects. You're going to have to deal with the different atoms at different temperatures, see different Rabi frequencies. Now we've gotten pretty good at this, so we can now do a pi pulse on a single atom. We can just repeat that many, many, many times, and we can show, whoops, the error in that pi pulse is about 7 times 10 to the minus 4. So we can have that single pi pulse be quite good on the population side. Of course, it's not just population you have to worry about, because you're doing this as part of almost like a entire gate, and you care about phase errors that accrue during that time. You have to be really, really careful with things like clock detuning and things like not just population error, but phase error as well. So this essentially 0.07 gets multiplied by a whole bunch of factors of 2. You have to deal with new kind of systematics, which is, things like if this transition is slightly detuned, you can have very, very good population effects. But if you actually look at what would end up being a single qubit phase on your 2Q gate, you can see that detuning shows up as changing that single qubit phase as a function of time. I think this is a little bit of old data, but you can see now we can play around with looking at this in a Ramsey sequence and figure out how much contrast, how much error, uncorrectable error are we actually having by doing this. And we obviously made this detuning error much worse to kind of show off what we mean when we say that single qubit errors kind of compound. Of course, that's only one part of it. You also need to do this on the Rydberg pulse, the actual entanglement operation. We can do this in the ytterbium system fairly easily, just looking at, putting atoms, like one atom in that interaction zone or 2 atoms in that interaction zone. And you can play games with that, and you can start to understand the flopping to and from the bright state, where you have one shared Rydberg excitation, and actually suppressing in this blockade radius regime the double Rydberg spectrum. Now, the nice thing about this is as you have this interaction zone, you can move the atoms farther apart or closer together, and you can kind of start to understand either an effective C6 interaction, or as you go to more complicated Rydberg spectrums, where that C6 interaction becomes more like a C to the third or C third interaction. But you can do this. I think we picked a very good state in this 65 triplet S1 state, and you can see this very, very nice sigmoid-like behavior that's very, very consistent with these like nicely behaving blockade interactions in this very, very strange unit of 120 gigahertz times micron to the 6th. So what does this mean for a 2-qubit gate? What does this mean for a 2-qubit gate? And also, I'm going to frantically search for a plug because my computer just said it was going to turn off. All right. When we look at this, it means that a 2-qubit gate involves a clock 180, a UV entangling pulse, and another clock 180, And unfortunately, it involves doing this on 2 atoms. So you have a whole bunch of factors of 2 that are going to affect your 2-qubit gate fidelity. However, this is a little bit old data as we've moved beyond Bell states right now. But when we set this up and tuned it up very carefully a few months ago, we arrived at something like this, 95% Bell state fidelity plus or minus 4. And we could try to do a much better job of dealing with spam measurements and things like that and trying to boost that up. In fact, I think if we did that now, we would see even a slightly better performance. But at the time, we understood that this was kind of a losing battle to figure out, what is the Bell state fidelity. You're just sensitive to many, many things that are not your 2-qubit gate. And so from there, we wanted to move on to essentially gate benchmarking. Whoops, I see different things are showing up at different times. So what we do is we utilize something similar to a global echo randomized benchmarking sequence. What this allows us to do is try out a few things. One is it allows us to quickly just tune up entangling phases of the UV portion of this. It also allows us to separate out the different portions of the gate, whether you're the UV part, which is this entangling part right here, or the clock parts. And in fact, we can actually come up with similar versions of this, which become sensitive to single qubit phases as well. The nice thing about this is it allows you very quick information about what you should be working on, whether it's clocks or whether it's UV pulses. And from that information and that close cycle of information, kind of understanding what we should be working on, over the course of the last few months, we've gone from doing our first 2-qubit gate on ytterbium now all the way up to about 99.4% 2-qubit gates on ytterbium, which as far as I know is one of the highest fidelities on neutral atoms, but also one of the highest fidelities for alkaline earths. I don't know if people have gone much beyond that. Interestingly enough, and this is something we're still looking into and trying to understand and understand its implications, if you essentially just focus on either the Rydberg part or the clock part, our Rydberg part, the actual entangling part, is only about 0.3% error in this recent gate. And similarly, the clock part is about 0.3% error. So we see that we have a lot of work to do to get to, say 3 nines, but at the same time, a lot of that error is not associated with the entangling part of the 2-qubit gate. About half of it is the entangling part, and half of it is the almost single qubit rotations of the clock itself. So this is an active area where we're pushing and also bringing the same thing up on the much larger system off to the side. So I went through that pretty quick. But I think I'm hitting that 45-minute mark pretty close. So I think I wanted to show off one last slide saying, thank you for inviting me. I'm happy to go over any questions. And yeah, this is the Atom Computing team, and we're always interested in bringing more people who look good in jerseys to Atom Computing. So, thank you.
Thanks, Ben, for this very nice talk. We have time for questions. So, thank you.
I have a question. So you mentioned this interaction region for doing 2-qubit gates. Does it take a very long time to bring qubits that are far away into this interaction region?
It does. I mean, I think movement is both a blessing and a curse. So you gain this huge amount of connectivity, which might be useful for different kinds of quantum error correcting codes, but now you're paying for it with the time. So I think that we have shown pretty similar movement speeds as to what's already been published by others, which is to say, state of the art is around order 100 microseconds. And I think that that's going to be a limiter. I mean, I think that there have been some recent papers by, I think there was a German group that recently published about trying to do optimal control for movements. But even then, if you were going down that route, you're only probably winning a factor of order 1 compared to about 100 microsecond movement speed.
Hi, Ben. Yeah, thanks very much. That was awesome. What is the parallel processing capabilities that you have? So can you apply, say, 50 CNOT gates at once, the entangling gates at once, in the same time scale?
So I think it goes back to this movement question. So if So there's a few different schemes we've worked with internally. One was to kind of prioritize connectivity, and one is to prioritize parallelism. I think there is a little bit of double side of the coin or whatever. I think that you could probably get to a scheme where you are just minimizing crosstalk and you're keeping atoms stationary, and you can do a fair number of 2-qubit gates in parallel. But then you have to actually do many, many rounds of doing 2-qubit gates. Because one of the kind of nice or bad things about these Rydberg systems is that the 1 over r to the 6th potential seems like it should drop off pretty fast, like r to the 6th, but it actually doesn't drop off that fast. And so if you want to minimize crosstalk for 2-qubit gates, you have to have keep out zones. But those keep out zones essentially make it so you can do something, I think it's on the order of like, you can split up your array into essentially, I think it was 24 or so, or maybe it's 36, I can't remember, different zones where you could do like 2-qubit gates in different zones. And so that's kind of, if you were going to do that without any movement, you could do something like that. With movement, I think right now its limit is just the number of interaction zones we have, which at this exact moment is about, I think, 16 interaction zones. So you're doing 16 2-qubit gates in parallel. But that being said, we also have plans to increase the number of interaction zones. Yeah.
Okay. All right, thanks.
Yeah, thanks for the nice talk. So you kind of briefly glossed over this, but you mentioned that the relative motion between the tweezers and the atoms, that's a common mode issue, so you kind of don't have to worry about it. And I guess my question is like, how true is that actually? And also, does the optical lattice hybrid, right? The optical lattice plus the tweezers, does that help with that at all?
No, it's the exact opposite. I mentioned that because we've now spent a lot more time working with the optical lattice hybrid. The common mode movement is pretty fantastic, and it forgives all ills or whatever. Whereas the optical lattice tweezer hybrid, it's kind of the opposite, because the optical lattice is formed by a separate piece of optics, and that optical lattice is very physically there and is like registered to very physical contact points. Whereas a lot of what you're doing through the microscope objective is now, it's all a question of how is that mechanically connected to the lattice. And so we see a lot more we have to be a lot more careful now, depending on what exactly we're doing, what is the effect of that. Now for 2-qubit gates, the effect is actually not that bad, because essentially everything we're doing with 2-qubit gates, we're using fairly large beams for. It's actually for single qubit gates that we see the biggest, challenge. Although we have gotten close to 3/9 fidelity on those single qubit gates as well. So it's a challenge, but not an insurmountable challenge. But I'd say it's, as the systems grow and complexity keeps increasing, it will be something we'll think about for future systems.
Thanks.
Right. More questions? The questions from the online audience, raise your hand. Oh, Henry.
Hi, thank you for the talk. So you mentioned this kind of at the beginning of the talk, but can you talk more about kind of the networking component? So the way I understand that is if you have multiple devices that are separated and you want to kind of run a really big computation that one can't support, you kind of try to split up the computation among devices?
Yeah, so we're taking not a completely wait and see approach, but what we're doing is we're trying to build the largest modules we possibly can. Because I think that even in a classical computer, the moment you ever involve a network, a lot of complexity comes and a lot of latency comes. So what we've started to look into are, building off technology we built on how to build in vacuum cavities and things like that. We're looking at schemes of creating distributed bell pairs, as fast as we can, and then using those distributed bell pairs to do teleported gates. So I think it's not an immediate push of ours. I think we've just started, and I think it's going to be a while until we have results that are particularly compelling, because I think that the networking aspect it's going to be take a back seat until we really hit a wall on a module size. Like, I think that right now it's pretty easy to see how we could increase the module size by, I mean, we were trying to increase the module size every time we build new systems by a factor of 10. And I think it's pretty easy to see how we can keep doing that for at least a few generations. Whereas building 10 times more systems to do that seems quite a bit more complicated.
Do you see the networking component as like kind of maybe it's a long term, but it's like a crucial step towards like ultimately solving like really large scale commercial problems?
I think that depends on who you ask, and I think it depends on exactly the amount of resources you need. I think that if there's been lots of advancements in recent quantum error correcting codes that have kind of gotten the physical to logical rate much, much better. And so I think it's a little bit borderline. Like, I think that it's a question of, can you build a module large enough, or do you have to build a module that has networking and build many modules?
Okay, thank you.
The question by Michael.
Yeah, hey Ben, how's it going?
Hi, Michael.
Yeah, so I had kind of a question about working with lasers kind of for a system that you would want to be kind of like run 24/7 or something like that. Do you see the technology advancing to the point where you could have kind of like automated tune-up of all of your parameters at some point where you don't need to have someone who's like a PhD in AMO physics kind of operating the system, and everything is just kind of you could automate most of the tune-ups that you kind of do on a daily basis.
Yeah, so we do that actually. So that's pretty much what quantum engineers are working on is they like build new measurements and then new ways of tuning things up, and then they create what we call is a Caliban node. So we have a system that does calibration called Caliban, and it essentially is a very just remove the person from the loop kind of procedure. And that's actually, I would say, it's, except for the actual building of the systems, that's what most people are doing is kind of improving different performances and then making sure Caliban is doing its job. I think that for lasers, I think we have some lasers that actually relock themselves. We have engineers that helped us build systems that were more robust than the physicist version that relock themselves. But even that, I would say we've decided that some lasers are better than others, and we have gone through multiple vendors and kind of ditched the ones that can't just stay locked for like weeks at a time. And I think that was a rough transition where we tried many different vendors and then eventually decided, not that I'll ever name a vendor, but like we eventually decided, oh, this vendor's no good. And we're just like gave up on that vendor and just moved on.
Hopefully I can meet up with you sometime offline and get to know all the good vendors. I had one more question about the 2-gate fidelities for the Rydberg end of things. Is it limited more by the Rydberg lifetime, so that going faster would help you, or is it actually laser noise on the Rydberg laser?
So actually, we're trying to answer that question right now. So what we've seen is that we've gotten to losses as low as just below, like I think it's like 0.1 loss per 2 cubic gate. And we think that a fair amount of that is a combination of what you just said, which is that as we go to larger and larger speeds, we're not seeing any wild benefit. And this is something that's only been true in the last few weeks. So actually, many of the things I just showed you actually were done at 5 megahertz, and we have about the same performance at 5 megahertz that we do at 15 megahertz. But I think that in the coming weeks, we'll see if by the time we go to DAMOP, if that continues to be true or not. But I think it's an interesting question because I think there's both finite block gate effects. If you've seen talks by Jeff, there's like lots of scary parastates. There's lots of overall questions of, is faster always better? And I think we have not yet answered that. We've also done some very careful calibrations, not calibrations, measurements of our laser noise. And the laser noise on that UV laser has been pushed way, way, way down to like few part 10s to 10 to the minus 4.
Great. Thanks.
We have one last question. If not, I would ask one short one. So you mentioned error correction, and there have been some impressive results in the past year from a different atom group. What's your plan going forward? And with all-to-all connectivity, what are the kind of codes you're thinking about?
Yeah, so I think we've been off and on, we worked with DARPA for a while on some specific sets of codes, and I think there's some things we're really excited about in those specific set of codes that are trying to just speed up logical computation time. I think it's really important to get mid-circuit measurement working in a way that's getting you beyond like error detection. So I think those results are kind of amazing. I put that Bluestein link there. I just think that the automated refilling and the essentially ability to measure without loss. We want to obviously bring those things together with a very impressive code demonstration soon. So, yeah.
Looking forward to it. I think then, unless it's something urgent, we'll thank Ben again, and then I'm sure he's also available.
Well, thank you for inviting me, Dave.
This was awesome. And I'm going to stop.